So I'm David Roundy, and I'll be talking to you today actually about a couple of subjects. I'm going to begin with a little about the talk. This isn't going to be an introduction for new users to Darcs, although I'll have a very brief introduction that won't assume that you have experience with Darcs. Darcs is a revision control system which, can someone turn down the mic? It's a little bit disturbing. Which is based on a formalism. Do you think this is? Should be someone on this one. I don't see. What? Oh, I'll just move it further. Okay, you can still hear me? Okay. Sorry about that. So, Darcs is based on a formalism for manipulating changes. And most of the talk will be, or half of the talk basically, will be on the subject of that formalism. The other half, which is all integrated together, will be describing a new trick that is being implemented in Darcs using what's called generalized algebraic data types to statically check a large number of properties of our code so that we can avoid, obviously, bugs, which I find to be very cool, but it's also rather confusing, potentially. So I'm a little bit hesitant, I guess, about whether for a general non-Haskell audience this will be appropriate. I'll try to introduce all the Haskell notation, all the Darcs notation that's necessary, but just bear with me as we go along. I'll start with an introduction to Darcs, then I'll introduce you to patch relationships, which is sequence, parallel, anti-parallel. Then I will introduce the GADIT subject, generalized algebraic data types, and how we use those to enforce the relationships between patches in Darcs code. Then I'll go ahead and describe the patch properties, and then finally show you how a merge is done in Darcs. So Darcs, as I said, is a change-based revision control system, which is in contrast to the more common history-based revision control systems. As far as its features, Darcs has a very friendly user interface, which is something that tends to surprise people. People oftentimes tend to hear that Darcs is based on quantum mechanics and other strange things. And get a little bit scared by it that it's going to be really complicated. But it's actually quite easy to use. It uses an egalitarian distributed model. Because of its ability to reorder changes, you can have very nice cherry-picking abilities. And it doesn't have merge points, which is something you see in, for example, Arch, or in Git even, issues. So just a few little diagrams. The centralized versus distributed model. This is perhaps obvious to people in this audience. CVS, subversion, etc. You have a centralized repository, everyone checks out from it. In the distributed model, which, for example, Darcs, Git, Bitkeeper, Monotone, or Arch, you have a number of repositories, and patches move freely in between them in any direction you want, which is much more flexible, and actually, in my opinion, is actually much more user-friendly way of working with things. But it leads to difficulties, or complexities, I should say, in terms of dealing with how you keep track of changes coming from different places in different orders. And Darcs uses a different approach than other systems. Essentially, every other system is what I would call a version-based system, in which, say, your history is viewed precisely as a history of different versions, is in that diagram. In Darcs, we would view that same history as being the addition of D to A, the addition of E to A, followed by the moving of A to B. We'd look at its changes, which then you can reorder these changes as you wish. And that's what formalism for dealing with that is what I'll be talking about today. To begin with a bit of terminology, I refer to change as a logical entity. So the same change may have different representations in different contexts. The patch is a description of a change. So a patch has to have a particular context. A patch, for example, would be add a line at line number 100. that would be an example of a patch. The state of a repository in Darcs is described by the set of changes in that repository. And this is a set rather than a sequence. The order doesn't matter. You'll get the same result regardless of order. The set of changes which is in a repository is actually stored as a sequence of patches, because each patch needs to have a context, and so they need to have an order. Then I'll describe a little bit of notation I'll be using this talk. I describe a change by some sort of capital letter A, and a patch would be represented by that capital letter with some possible prime or subscript for if it's a different context of the same change. The state or the context, I use state and context almost interchangeably. They both indicate in the Darcs picture the set of changes that are already in the repository. And I represent the state of context for a given patch sometimes using this picture where you have A as the patch, starts in state A, starts in state 0, ends in state A. And that's used when we need to annotate the relationship between various patches more carefully to keep track of things. And actually, this information is the information that is going to be stored in the gadgets when we have type checking, which will check that you don't ever improperly use a patch in the context in which it should not be used. So, just to reiterate, the fundamental paradigm of Darcs is that the state of a repository is always defined by a set of changes. And the formalism I'm going to describe is basically a formalism that allows us to guarantee that the same set of changes will always give you the same repository, regardless of what order and how you got to that set of changes. So that is that. So patch relationships. Patches are normally stored in sequence, and so sequential patches I write as A, B, C, as you might imagine, meaning A first, then B, then C. If you annotate the states, it would look like this. A takes you from O to A, B takes you from A to B, C takes you from B to C. In Haskell, when we write this, we use infix operators. They're actually constructors technically in Haskell, and I have a couple of them depending if you have just two patches, we use that dot notation for A followed by B. If you have multiple patches, we use this notation. And I will be going throughout the talk and showing you both sort of a mathematical approach for describing something, and then showing you in Haskell what it looks like. Haskell has the nice feature that you can define sort of arbitrary infix operators, which can make your code a little bit confusing, but it's better than overloading plus to mean insane things. So the second state relationship that the pairs of patches can have is they can be either parallel or anti-parallel. And parallel is sort of a misnomer. Parallel patches start at the same state and then both diverge. They do slightly different things. Anti-parallel patches start at two different states and then come to the same state. So generally, when you get an anti-parallel set of patches, usually it comes from inverting a pair of parallel patches. So in this picture, A, which goes from O to A, a little confusing, and B, which goes from O to B, are two parallel patches, and the inverses of them are anti-parallel. And I write this mathematically. We use this V notation for parallel, meaning they start at the same place, go to different places. For inverse anti-parallel, we use the opposite notation. And the Haskell notation is strongly influenced by that, looks basically the same. The colons, in case you're curious, indicate that these are constructor-type operators, which is important, but doesn't matter if you don't know Haskell. So, to move on to enforcing the patch relationships, the GADIT work that I will be describing is something that came about when I went to ICFP this fall. I met with a few people and heard a few talks about theorem proving in software, and we spent the week working out how we could enforce the patch relationships by the type system, because Haskell has a very strong type system that includes type inference, so you don't have to actually annotate all of your types in order to get the full type checking. So what we're using is what's called generalized algebraic data types. They're a new feature in Haskell, and actually the released version of Haskell it has a bug in it, so you really have to use the Darcs version of Haskell, the one from their Darcs repository, if you wanted to reproduce this. The generalized algebraic data types allow you to restrict the type of an object at runtime and have that be statically checked, which I'll show you in a bit. The common use examples for generalized algebraic data types is for representing an abstract syntax tree, in which certain parts of that tree may have a different type from others, and you can get very strong type checking this way. Let me give you a brief introduction to the syntax in Haskell. Types always start with an uppercase letter, as in int, capital int. Functions are always lowercase letters. Then this is an example of how you declare the type of a function. This is a function foo, which accepts an int argument and a char argument and returns a bool. Okay? The reason for the somewhat strange-looking syntax is that you can also view function foo as a function that accepts an int argument and returns a function that accepts a char argument and returns a bool. You can also, in Haskell, you can have lowercase letters representing type variables. So in this case, function bar, these are in the place of a type. So A here is an arbitrary type. And this is a function that takes an object of any type and another object of the same type and returns a third object of the same type. In practice, you can't write a very interesting function bar because you always have to return either one on the left or one on the right. But it's a simple example. So to move on to algebraic data types. Algebraic data types in Haskell are, for example, bool, which is declared data is a bool type, where you have two what are called constructors, true and false, which are bool. The syntax I'm using here is the Gaddit syntax, which will be new to any Haskellers out here who aren't familiar with Gaddits, since it's a new type. Another example would be data complex, which could have three different types, and these are called constructors. You can have Cartesian, which takes a double and a double, and is a complex. And what that means is that if you want to construct a Cartesian type of complex number, you just type Cartesian 1, 2, and you can then have polar, which takes a double and double, or something like, say, a pure real, which has only a double in it. This is sort of what types look like. Algebraic data types also allow you to have arbitrary types involved in them, and this is where we start getting more interesting. So a maybe A here is a type variable, which has then two constructors. This is in standard Haskell. One of them is either you have just an A, or maybe you have nothing. And the type of each of those is maybe A. Okay? This is how we can define somewhat more interesting types. To get now to generalized algebraic data types, I will define, here we have a pair AB. And we can have pair AB has two possibilities. It can either be the first thing, which is a pair which has an A and a B in it, or it can be and that has type, whoa, I have typos there. So that should not say foo AB, that should say pair AB in both of those cases. Obviously, I changed my mind in what I was writing. So the second possibility is what's called a symmetric pair, which is AA. And that gives you a pair AA. And this is where the power of algebraic data types comes in, is that the symmetric pair has a more restricted type than the pair does. It's also a pair, but it's a pair in which both of the two objects have the same type. And so this allows us at runtime, when we're given a pair, to look and see whether it's a symmetric pair or a pair, and that affects the type system, and we have static checking of this. And so we can write a function like this, which is foo, which foo takes a pair AB and it returns a B. If you have a pair XY, then it has to return Y because Y is the only object here with type B. But if you have a symmetric pair XY, we know that the two have the same type, and so we can return X instead. And that's the simplest example I could come up with of how you can use gadgets to do interesting type stuff. And so now just a little bit of discussion of what's going to be coming up, which is that in Darcs we're using phantom existential witness types, which sounds rather spooky and feels rather spooky at times too. Phantom types are types that don't actually exist, which means that when you compile them, there's no runtime cost because they don't have any objects they're instantiating. Existential types are types whose identity you can't determine, which means that you can make it impossible for someone to generate a new object of the same data type because it's existential and they can't know what the same type is. And that allows us to do strong, to enforce restrictions on what people can do with our code. People meaning Darcs developers. Finally, witness type is any type whose existence proves some property. And we'll be using all of these to make Darcs easier, harder to write bugs in Darcs. This approach catches probably historically, I would estimate something like what have been 95% of the important bugs that have shown up in Darcs would have been caught if we had this earlier. So the first patch property is inversion. Every patch in Darcs has to be invertible. And you have to be able to invert that patch knowing only the patch itself. You don't have to look up the repository state. So the repercussions, for example, a remove file patch either has to contain the contents of the entire file, or in order to invert it, or the file that you're removing has to already be empty. In Darcs, we take the latter approach. You can only remove a file after it's been emptied. This also has repercussions that patches such as copy file, which are implemented in Subversion, are extra complicated since inverting a copy file comes to some sort of a merge file patch, and figuring out the semantics of a merge file patch would be very complicated. Another feature is because patches are invertible, we can apply patches either forwards or backwards, and there are going to be other benefits we will see when we start merging, assuming I finish in time. So I'll show you where the phantom types come in. The patch type is defined as a gadget with a form patch AB, where A and B are the initial state, represent the initial state and the final state, being phantom witness types, existential ones. And so when we write the function invert has the type patch OA becomes a patch AO. And this is represented in the mathematical picture. Your original A was going from O to A, but when you invert it, it goes from A to O. So this is the sort of simple picture of where we, how we can use our code becomes more descriptive when we have these phantom types hanging around. The inverse of a sequence is, as you might imagine, inverse of ABC becomes C inverse, B inverse, A inverse. Then in Haskell code, if you can either invert A followed by B followed by C, or you can invert them in the other order, you get the same result, as we will see. So moving on to patch equality becomes a little bit trickier when you're using these gadgets, because if you have two patches that aren't necessarily equal, they don't have the same type. And comparing things with different types is somewhat scarier. But what this represents is a real issue and a real possible bug in Darcs. That in order if two patches are equal, then it means that their representations are the same, and the initial state is the same, and the final state is the same. If any two of those properties are true, you know that the patches are equal. But you have to know that two of them are true. Just checking that the representation of the patch is true is not sufficient to know that the patches are actually equal. For example, something modifying the 100th line wouldn't be the same patch if it's occurring after something had been added at the beginning of the line, because the 100th line would represent something different. So what we need is a function that accepts two parallel patches and determines if they're equal by comparing the representation, and we need a function that accepts two anti-parallel patches and determines whether they're equal. And then my note is what I already said. So we can do this using gadgets to determine the type equality. So we can define a data type equality check of A and B. And the not equal will have type equality check A and B, but is equal will have a type equality check AA. This is a way we can assert at runtime, based on a comparison of representations, that two types are the same. So we can take two of these phantom existential witness types and force them to be the same, and the compiler will, we implement this using unsafe, as I say, unsafe coerce. So these are our two equalities. We have the sort of the symbol for parallel and anti-parallel, and they check two parallel patches and return an equality check. So here's an example. You have a function which accepts a couple of parallel sequences, and then what it's checking here is it checks if these two parallel sequences A and A prime are equal, then you can do some other function, and you know that B is parallel to B prime because they both came after equal patches. And just this construction here will fail if we didn't have this equality check, which enforces that A and A prime have the same ending state, which then enforces also that B and C have the same beginning state. This is the mathematical picture. You say AB is parallel to A prime C. If A is equal to A prime, then B is parallel to C. And that is checked by the code there. If you had not eq instead of is eq here, this would fail in the type checker at compile time, which is very nice. So to move on to actually doing interesting stuff, most of Darcs' work, well, inversion is very important, but most of the work is done by the commutation function. The commute function is both a relationship and a function which takes two sequential patches and reorders them so that well, the second one comes first. Mathematically, I write this using this double-headed arrow, which is a little bit confusing at times, but it's because it's both a function and a relationship. In fact, it's also a self-inverting function, so that if AB commutes to B prime A prime, then vice versa as well. And you can note here, when I write down the context, there's a strange context that comes in here, which wasn't known beforehand. And this is a new existential context that is generated by the commute in the checking. So the way it works is it takes, Haskell function-wise, I should mention, commutation can fail. If you have two patches like first add a file, then remove the same file, recommuting those two patches is not going to be very meaningful, in which case commutation fails. And how much time do I have? 10 minutes? What? Plenty? Okay, good. So in this example, this is the Haskell do notation, which allows you to do a series of calculations that might return failure. And if they return failure, the final result returns failure. So you take some sequence of patches, A, B, C, which are sequential. Then you can commute the pair of patches A and B, which are known to be in order. That gives you a pair of patches B prime and A prime. And now A prime, now because it's, because A prime is the commute of this sequence, A prime now is in sequence with C. So we can now commute A prime with C and check that it commutes properly. And with these witness types, if you made a mistake of putting any of these in the wrong order, you would get a compile time error, which is, and when we first started implementing this, it was very entertaining. The first time it got it working, actually, Ganesh here, I got it working, and he's like, dang it doesn't work. I still haven't got it working. But it was because he had an error in his code that he was using to check it. And once we reordered the commute, it worked, and it was quite a relief. So the property I mentioned beforehand, commutation, when it's successful, is self-inverting. This is obviously needs to be true, but it's also sort of easy to write bugs so that it isn't. So I just have an example here of what Haskell code would look like to verify this. You can verify the commute of A followed by B, where the commute succeeds is what that is just says. And then you just say, you commute A and B, you get B1A1, you commute B1A1, you get AB, and then you check that they're both equal. And this is, and in the second case, we could actually use either version of equality because we know that they sort of both have the same starting and ending states. This is just sort of an example of what the code looks like when you deal with these nice, well, to me it looks nice. To non-Haskellers, maybe it doesn't look nice. Next feature is the commutation of an inverse sequential pair. If you have a pair of patches AB and they commute to B1A1, if you were to instead choose to commute the inverses, B inverse, A inverse, it will commute to the same pair of patches inverted, A inverse, B inverse, A1 inverse, B1 inverse. I mention all these properties because, well, they need to be right. And we have lots of checks to make sure they're all right. And if you don't have all the properties right, you end up with sometimes very subtle and hard to find bugs that only show up in very obscure scenarios. So just, I think it's probably not worth talking you through the code for verifying this. It's similar to the previous function I just walked through. And you can look it up. I'll put these on the web somewhere if you're interested. So finally, this is the trickiest property to get right. No, it's not the trickiest property, second trickiest. The trickiest one comes next, which is commutation of a patch with both a patch and its inverse. If you take B and A and you commute them to get B1A1, and then if you take this B1 and you commute it with A inverse, what I'll now have done is this patch will have commuted by A and A inverse, which is roughly like commuting by the identity patch. And as a result, B needs to return to become the same original B again. This A inverse will become A1 inverse, the same patch inverted. This is a very important property which seems obvious and is usually true if you just use your intuition to write commutation code, but actually is violated in the presence of conflicts by the current version of Darcs. And this is one of the features we're working on improving in the next major version, will be to make the conflicts obey this property, which will add much nicer user interface when you have conflicts. And again, I think I'll just skip over the example of the code example of how we verify this. So the final, and this is the trickiest property, is what we call permutivity, which is a word I made up because we don't know of any mathematical word that means the same thing. And what that means is that, let me just read it. It's the property of the commute, which means that every commuted permutation is uniquely defined regardless of the order in which you do the permutation. And what this means is if you commute the patches A, B, C to switch B and C, to switch A and C, to switch A and B, to switch the others. There are multiple orders in which you could go to get to each of these permutations. And however you do the commute, you need to get the same answers. This is, of course, crucial for the property which I said with how Darcs works, that the state of a repository is defined by the set of changes in the repository. And fortunately, we have a proof that if any set of 3 patches satisfies permutivity, then any set of n patches sequence of n patches will also satisfy permutivity. And so that would be by Ganesh, as I point out here. And I should point out this only applies to permutations that actually exist, in the sense that if the commutation fails, you can't make every permutation. And so you don't have to worry about the ones that are impossible. So this is, again, an important property which is a little bit tricky to verify, because you have to generate lots of, not to say I don't believe it's satisfied, but it's hard to prove it's satisfied, which is a little bit frustrating. So I will just now go to, finally, the application. Once we have all of these properties, all I've been talking about was patches in order, permuting, or commuting. But a merge now comes out straightforwardly, or relatively straightforwardly. A merge is when you take 2 parallel patches, like I make a change and you make a change, and you want to convert them into a pair of sequential patches, my change first, your change second. Or your change first, my change second, depending who's pulling. And the commutation of that sequential pair that's generated by the merge has to be able to reconstruct both of the original patches, which is to say, if my change is A and your change is B, then the merged result, my change and then your change, when I commute them, had better be your change than my change, where this B is your original change, this A is my original change. And fortunately, by the property, the second to last property I showed you, which is the commutation of a patch with its inverse, with a patch and its inverse, we can easily see that this is true if this is true. And in this case, where we commute A with B inverse, now we can just compute this because we know both of these 2 patches on the left-hand side. And as I said, commutation is a function, so we can just apply that function and we determine both of these 2 possible merges depending on which one we want. That is the algorithm for doing merges, and I should maybe briefly point out the current Darcs code. So you might wonder, what happens if the commute fails? If the commute fails, then we can't use this algorithm. And in the current Darcs code, what we then do is we use when a commute fails, that means it's got a conflict. In the current Darcs code, we hand generate a special patch which is constructed in such a way as to satisfy this relationship, a special patch called a merger. In the next generation, the plan is to have a special version of commute that always succeeds and generates something equivalent to those merger patches just by making this commutation always succeed, and if they would fail, then it generates one of these special patches that has sort of artificially constructed commutation behavior, which is constructed in such a way as to satisfy all of these properties. So to briefly show you the code to do them, wait, what just happened? Didn't I just show you that? Okay, merge, I guess that's reiterating what I just told you, which is a little odd. I didn't. So here's the code now to generate, to run the merge. If you have 2 parallel patches, A and B, it gives you, this 2 parallel patches, it gives you anti-parallel patches, B and A, which is to say that the original patches A and B are parallel, but the final patches B1 and A1 are anti-parallel, because the final state of both merged possibilities is the same final state. And so what happens is you merge two parallel patches, A and B. You do that by inverting B and A, taking it with A, and then you commute. That gives you A1 and B1, which you can then invert the A1 and the inverse of B1. And you commute, or you don't commute those, you return them. And that is how we do a merge. It's actually very simple. And maybe at this stage I should mention, many people tend to like to think of merging as being the primitive operation in a theory like this. And the reason we prefer commute as a primitive operation is it has all of these nice properties that we described. You could rewrite them in terms of merges, but it's all much more complicated when you rewrite it in terms of merges. Because, for example, the commute is a self-inverting function. When you rewrite that in terms of merges, you have to invoke many different merges to rewrite the same properties. It's a much nicer picture. So I've actually reached the end, perhaps early, which will mean more time for questions. Just to reiterate this quote I said, that's what we found when working on these Gadet type checking thing. Whenever we ran into a problem where we said, this is not possible, we cannot figure out how to solve this, the solution was always to create a new Gadet. For example, the equality business, we spent ages trying to figure out how to deal with patch equality because we had these different types that you're comparing. And finally, we found out that if you just use this Gadet, this is-eq or not-eq, everything's beautiful and easy. So if you ever get a chance to use Gadets and use really advanced Haskell, it's lots. And just one note for any Darcs users here who want to talk with us, there are a number of developers present, about what features are more important to you or issues, then you can meet outside of this building at 1 o'clock or whenever the Valgrind talk ends for lunch, and we can talk about that. So, questions? Or
which has an initial state which is type A and final state which is type B. So if A and B have no instantiations, what are instantiations of the type pair AB?
Okay, so the question was, I'm using phantom types for patch AB, where A and B are types that have no instances, yes. And so then the question is, when we do pair AB, or patch AB,
that depends on two types.
Then the question is,
what are instances of this type?
What are instances of the patch?
Yeah, and how these types are used.
So I've simplified some of the code at places. One of the tricks you can use with these phantom types and these existential types is you can create a new Gadet, that being the solution to every difficulty, which seals up a patch. And so when we get to putting this into the actual Darcs code base, we will have, well, every repository will start with a void state, which represents nothing. And the final state will be an existential. And when you seal it up like that, then you can instantiate without any worries about what the A and B are, because they're existential.
So the instances of patch A have nothing to do with A and B?
Yes. Yes. The actual data involved doesn't have anything to do with A and B. Okay, I think I see what you're saying. In Darcs, you tend to have, in CVS you have one big repository which has everything that you own in it. In Darcs you have generally many small repositories, one per project. And so if you wanted to throw away one of those entirely, you could, because there's all separate repositories. I think, is that answering your question? Or, I mean, if you delete files from Darcs, then deleting them takes as much space as they took originally, but then you don't have to worry about them anymore.
I have a similar worry. I really love Darcs, but each time I add a new file, I think twice, because I know it's going to be there forever. And I wish there would be a way of extracting a sub-history of my repository that would not contain that file and all the effects of that file being present. I'd be looking for a kind of purge this change and everything that depends on that change. I think it's kind of what you said.
Okay, so that was, I'm supposed to repeat everything for the recording. So what he was saying was he's also concerned about this. Every time he adds a file in Darcs, he thinks twice because it's going to be there forever in the history, and he wishes he could just expunge it, something to that effect.
From time to time, okay, what's great with Darcs, it allows you to travel back through time and remove things, but let's assume that I have created a patch which creates two files, and I have recorded it. And if I record later patches which depend on that patch, and if later on remove that patch, I was not careful enough to make two patches. I made one patch. So I like to go back in time, split that patch in two, and split everything that depends on it so that I could unpull the patch that created the wrong file.
Yes. And what he's saying, to briefly reiterate, one of the nice features of Darcs is that you can do a lot of manipulation, removing things from your history, because it's not history-based, it's change-based, and if you eliminate changes, they're just gone. But the trouble is if one change depends on another change, which is to say if they don't commute, and so if you want to remove part of a given change, a particular file, then you're in trouble. And I'm afraid I don't have a solution to that, except to be really careful the first time.
Yeah, it would be something for the brainstorming, but also I have sometimes the opposite need. I like to have patches which have sound semantics.
Right.
Sometimes I have two small patches which I would like to merge, and I guess I could do it by replaying the history like those CVS to Darcs tool works. I have a repository which contains 1,400 patches, but it started life as CVS, then a bit cheaper, then after the mishap. So it's kind of feasible by replaying the history at some point.
Yeah. Obviously, since I created the unpull command, I'm comfortable with modifying history, but too much modifying history disturbs me because I'm afraid that you do it wrong and you're hosed, and that's frightening.
I would like to go back to the essential parts. You said it's close to
I'm sorry, could you repeat?
if I remember well, you said that the
Exist.
type is a type whose identity cannot be
Right, determined.
What is the identity of a type?
Well, I mean, whether it's an int or a bool or I.
Oh, so it means that you can compare that type to another type.
Yes, is that?
Equality of types is not decidable if this type is involved.
Right.
Okay.
Yes. And I should say that I'm not all that strong in existential phantom witness types. I know how to use them, but I don't know. It's sort of intuitive on my part at this stage.
I read that at some point you wrote a C++ version. I'm just discovering Haskell, but it seems to me that those kind of specializations on types is very like multi-methods, actually. Or
like what?
Multi-methods. It's methods which depend on more than one type. Like you have that in CLOS and in Perl to through a module. For example, if a cow meets a wolf, the cow runs away. If a wolf meets a cow, it tries to eat the cow, and if two animals meet, usually they ignore each other. So multi-methods are kind of virtual functions which depend on more than one dynamic type. But you can view them as kind of rules. And you simply select the most specific one. And like C++ partial specialization.
Uh-huh.
It's the same kind of idea. You've done C++ programming. Have you played with that?
I have not played with that, and that's one of the things that scares me about C++, is that I've been programming in it for an awful long time, and it seems like I know only a very, very small fraction of the language, which I guess...
And you've never played with Common Lisp and Silos?
No, I haven't. Any other questions? Or we need...
So each patch should be reversible, but then when you delete a file, to be able to invert this patch, you need to store somewhere the contents of that file. Does that mean that each time you delete a file from a repository, you store the contents of the file?
Yeah, so in Darcs, when you delete a file, it actually is two patches. One of them removes the content, so it becomes an empty file, and the second one deletes it. And so that adds, it adds overhead for storing it, but it also adds redundancy that if one of the patches gets deleted somewhere in your history due to disk corruption or something, you can apply backwards your history back to that point, which is maybe not necessary if you've got good backups, but at least makes me feel more comfortable. Right. So the main big problem with Darcs currently is conflict handling. And that's something that, unfortunately, turns out to be a hard problem. And so we are working on that. Well, I should also point out, for those who aren't familiar with Darcs, the conflict handling still, in current Darcs, works well enough to be quite practical. But sometimes you run into trouble where it becomes exponentially expensive. And sometimes you run into trouble where Darcs can't handle the conflict and can't figure out what's going on. Because when I wrote that code, I spent a long time, but couldn't figure out how to make it always work. So we're trying to be much more careful this time and make sure that we can make it always work. We have some good ideas, and there are people somewhere here who are helping me with it. And I'm not sure time frame-wise how long that'll take. As far as plans for other things in Darcs, we've been talking about adding checksumming and for verification, what other sorts of things are going on. New patch types are always interesting. For example, line-based patches are great for code, but for LaTeX files like my talk, I'd rather have word-based patches, for example. Does that answer sort of the...
Well, I was just wondering, when I was on the website, they had the impression there wasn't much activity.
Well, there's, on the conflict side, it's largely pen and paper with a bit of coding in a separate repository. Certainly things have slowed down largely, I believe, because Darcs does what, apart from the conflicts issue, which isn't going on in the main repository, most people seem to be largely satisfied. I'm satisfied with how Darcs works at the moment. And so there are a number of people making changes, but not all the time.
Was there, is that a rumor about this Git backend or something like that?
Git backend? Yeah, so that's one of the things actually sometime later today I'll be talking with Julius, one of our developers, about. Well, he's been busy. Real world stuff. But he expects to have time for that in the summer. So that's very interesting. Interfacing with Git is very interesting because Git has a very nice, very clean, and almost completely opposite to Darcs' way of looking at things. And so, yeah, that'll be fun to get that.
What would be fun would be to have an API to allow me to create new kinds of patches. I have several ideas like compile patches.
Yeah, so the trouble with creating new patch types, this is sort of the patch plugins idea. And it's very appealing, but you have to get all the commutation right. If you make a mistake in your commutation, you get repository corruption, and that's very bad. The other issue is that generally speaking, if you have n patch types, you need n squared commutation rules for how each patch type commutes with every other patch type. And so when you've got plugins, now of course you can always say that, you know, my new patch type doesn't commute with any other patches, and then it's only order n, you know, one commute rule for each patch, each plugin, which in practice is maybe what you want to do. You know, because if you have XML patches, you don't want to intermix those with line-based patches because they aren't going to commute. But there are a lot of complexities there that make it a bit scary. And so, yeah. Okay, I guess that's all.